Welcome to a screencast on balancing oxidation-reduction reactions in acidic solution. The objective of this screencast is for you to be able to write and balance oxidation-reduction reactions in acidic aqueous solution. And the example we will use is the reaction between copper solid and the nitrate ion to make copper 2 plus ion and nitrogen monoxide gas. And we're going to balance this reaction in acidic aqueous solution. Now, the first thing when we have a redox reaction is we usually want to figure out what was oxidized and what was reduced. Sometimes that's pretty straightforward. You can just do it by inspection. For example, here, copper solid forms the copper 2 plus ion. Copper clearly loses electrons and is therefore oxidized. But sometimes it's not as easy to see. You might not be able to look at the nitrate ion and nitrogen monoxide and immediately see the transfer of electrons. In this case, it's often best to go to oxidation numbers. So let's just do the oxidation numbers for all of the substances in this reaction. And from left to right, copper, the element, has no charge, so it has an oxidation number of 0. In the nitrate ion, oxygen is expected to have an oxidation number of -2. And since there are 3 oxygens, that's a total charge of 3 times -2, which is -6. And then nitrogen has to have an oxidation number that, when added to -6, adds up to the overall charge of this ion, which is -1. And so that, of course, would be +5, because +5 plus a -2 times 3, which is -6, adds up to -1. Now, copper 2 plus has a charge of +2, so it has an oxidation number of +2. And in nitrogen monoxide, the oxygen is going to have an oxidation number of -2. That means the nitrogen has to have an oxidation number of +2, so that the +2 and -2, the total charge, ends up being 0 for this neutral compound. Okay, so if we consider what happened to the copper, its oxidation number went from 0 to +2. Oxidation number increasing corresponds to oxidation, so copper was oxidized. Now, the other element that had its oxidation number changed is the nitrogen. It went from +5 oxidation number to +2 oxidation number. That's a decrease in oxidation number, and so nitrogen was reduced. And then note, the oxygen did not have its oxidation number changed, so nothing there. Okay, so we know now what was oxidized and what was reduced. And what we do is we separate this overall reaction into half reactions, and we balance them separately first. So the oxidation half reaction is copper solid forming copper 2 plus. So we write out that part of the overall reaction as the copper or oxidation half reaction. And then to balance this one's pretty simple to balance, because all we have to do is note that when copper solid makes copper 2 plus, 2 electrons were quote-unquote lost from the copper. So we have to put the 2 electrons on, in this case, the right-hand side, so that this overall half reaction is balanced. Copper solid forms copper 2 plus and 2 electrons. Okay, that was an easy one to balance. Now let's look at the reduction half reaction, and that is the nitrate ion, NO3-, forming nitrogen monoxide gas. Now, to balance this is a little bit harder, but not too bad if we think about what's going on and are a little careful. First of all, we want to make sure that all elements other than hydrogen and oxygen are balanced. So that, in this case, would be nitrogen. There's 1 nitrogen on the left, 1 nitrogen on the right, so that is already balanced. If we had an imbalance in nitrogens, like let's say this was N2O, then we'd have to put a 2 out in front of the NO3-, so we had the same number of nitrogens on both sides. Okay, but in this case, nitrogen's already balanced, so next we move on to balancing the oxygens, and notice there's 3 oxygens on the left from the nitrate, and 1 oxygen from the nitrogen monoxide on the right. So they're out of balance, and we clearly can't put coefficients in front to make things balanced, because that would affect the balance of the nitrogens. But if we note we're in aqueous solution, that means we have water. And if there is water around, that can actually participate in the reaction. And so if we add 2 water molecules to the right-hand side of this reaction, then we have 2 more O's added to the O from nitrogen monoxide. So we have 3 total O's or oxygens on the right, balances the 3 total oxygens on the left. Okay, so we've now balanced the oxygens, but we've introduced some hydrogens. Now we have 4 hydrogens on the right-hand side of the equation. We have to have 4 hydrogens on the left-hand side of the equation. But now, if we note that not only are we in aqueous solution, but we're in acidic aqueous solution, that means we have hydrogen ions floating around. So, to balance off the 4 hydrogens on the right from the water, we add 4 H+ ions to the left to balance off the hydrogens. And now the nitrogens are balanced, the oxygens are balanced, and the hydrogens finally are balanced as well. And so the only thing left to balance is charge or electrons. And if we note on the right-hand side of the reaction, there's no total charge. Nitrogen monoxide and water are both neutral. And on the left-hand side, we have a -1 from the nitrate and 4 positive ones from the 4 hydrogen ions. So that's a total of +3. And so that whole side of the equation has to be neutral, same as the other side of the equation. And so we can add 3 electrons to balance off the +3 charge from these 2 substances, and that balances charge on the 2 sides of this half reaction. Note that to balance charge, we're always adding electrons or negative charge. A couple other things to note. If one of your half reactions, the oxidation half reaction, has electrons on the right, which it will if it's an oxidation half reaction, the other half reaction, the reduction half reaction, has to have electrons on the left. One other thing to note is we can balance electrons by balancing charge. We can also look at oxidation number and note that the nitrogen had its oxidation number go from +5 to +2. That corresponds to a decrease of 3, which corresponds to 3 electrons. Okay, so now we have each half reaction balanced separately. The oxidation half reaction is balanced, and the reduction half reaction is balanced, and we need to combine those 2 half reactions. Now, notice to do that, we have an issue here. 2 electrons for the oxidation half reaction, 3 electrons for the reduction half reaction. And we can't have a different number of electrons lost and gained, so we have to make the number of electrons equal. And how do we equalize 2 electrons lost and 3 electrons gained? Well, if we triple the half reaction for oxidation, triple both sides of it, of course, and double the half reaction for reduction, double both sides of that, then when we multiply this through by 3, we'll get 6 electrons for the oxidation. And when we multiply the reduction half reaction through by 2, we'll get 6 electrons for that. So the oxidation half reaction multiplied through by 3, you multiply each coefficient by 3, and we get 3 coppers, makes 3 copper 2+ and 6 electrons. And then with the nitrogen, the reduction half reaction, we do the same thing. We multiply each coefficient by 2, so that becomes 2NO3- plus 8H+ plus 6 electrons makes 2NO plus 4H2O. And if we did everything right, then the electrons on the right of the oxidation half reaction and the electrons on the left of the reduction half reaction will cancel out. And then we simply add together the 2 half reactions, to get our overall reaction. And that works out to be 3 copper from the first half reaction, plus 2NO3 minus from the second half reaction, plus 8H plus also from the second half reaction, and that forms 3 copper 2 plus from the first half reaction, 2 nitrogen monoxides from the second half reaction, and 4 H2Os from the second half reaction as well. Now, in this particular example, we simply add everything up, and after canceling the electrons, nothing else needs to cancel. You can have situations where, for example, there's 4 H2Os on the right of this reaction, and there's maybe 1 H2O on the left side of this half reaction, and in that case you do cancellation as well. 4 H2Os on the right with 1 H2O on the left would leave an overall net of 3 H2Os on the right. So it might also be possible you have to cancel out some H pluses and or H2Os. But in this case, we didn't. So to summarize the general method for balancing oxidation-reduction reactions in acidic aqueous solution, first of all, we need to identify what substance is oxidized and what substance is reduced. And usually we do this via oxidation numbers. You don't have to, but likely. Then we write the unbalanced oxidation and reduction half reactions, and of course we keep them separate. And then we balance each half reaction separately. First we balance elements other than hydrogen and oxygen. Then we balance oxygen, and we use water to do that. Then we balance hydrogen, and we use hydrogen ion to do that. And then finally we balance the charge, and we use electrons to balance charge. And then once we've balanced each half reaction, we multiply each half reaction by the appropriate factor to make sure that the electrons or the charge is balanced. And then we add up the half reactions. And if there are common terms, we cancel out the common terms from both sides, and we simplify our reaction. And at that point we're done. We've balanced the redox reaction in acidic aqueous solution. And that is it for the Balancing Redox Reactions in Aqueous Solution screencast.